Good morning all of you. Today we are going to discuss very important theorem, that is Lagrange's theorem. This is one of the essay. We have to write statement also. The question is asked as state and prove Lagrange's theorem. So let us consider the statement. What is the statement? The order of a subgroup of a finite group G divides order of that group. What is its meaning? If H is a subgroup of finite group G, then we want to prove that H is, in other words, we can write if H is a subgroup of finite group G, then we want to prove that order of H divides order of G. This is the statement. For that, what is the given in the statement? H is a subgroup of finite group G. So, one is the finite group, another one is a subgroup given. Let us consider it as a hypothesis. Let G is a finite group. Whenever it is a finite, we can write it as a set notation consisting finite number of countable number of elements. Let them be E, A1, A2 and so on, An minus 1 with a finite group with the identity element, first element treated as an identity here. Okay, what is its order now? Let us count the elements A1, A2, A3 and so on, An minus 1. They are nothing but n minus 1 elements including E. Additionally, we add one element, that means totally how much elements are there? There are n elements. So, clear here order of G is n. Now let us consider H be any subgroup of G. Okay. Whenever it is a subgroup of G, how many kinds of subgroups are there? There are two kinds. In each case, we want to prove that order of H divides order of G. What are the subgroups? Kinds of subgroups? They are nothing but proper subgroups and improper subgroups. In the case 1, let us discuss when H is any proper subgroup. Initially, we have improper subgroups, we can count them. They are for any group, the subgroups, improper subgroups are 2. They are singleton E and G itself. Whereas in proper case, we can't find them. So, we can treat it generally H be any subgroup. Okay, right. Now, coming to the hypothesis again, G is a finite group, then H is also finite because it is a subset of finite set. H is a subset of finite set. H is a subset of finite set. G is finite, obviously H is finite. So, H is finite. Whenever it is a finite group, subgroup, then its order is finite and treat it as M. Now, we have two results we can use here for our convenience. The first result is that there is a one-to-one correspondence between any two right cosets, or right or left. I am considering here right. Any two right cosets of H in G. What is the meaning of this? You have an idea of sets and relations, mappings. One-to-one correspondence between means bisective mapping between any two right cosets. Suppose HA and HB are two right cosets. F being, if you are considering mapping from HA to HB as F of HA is equal to HA inverse, then obviously this mapping is a bisective mapping. Whenever the function is bisective, which means generally the domain, what is this, is called domain. domain and codomain. Any function consisting domain and codomain, isn't it? Any bisective functions gives the result as the number of elements in the domain is same as the number of elements in the codomain, which means order of HA is equal to order of HB. Now coming to the statement, we know that there is a one-to-one correspondence between any two right cosets. If you consider HA, HB, whatever it may be, here we can considering so many cosets are there. Any two right cosets consisting same number of elements. This statement says that any two right cosets consisting same number of elements. From the we can easily conclude that order of HE. What is HE? Regarding to each element in group, we can write a coset. So first element, regarding to the first element, we have HE. This is a coset generated by E. So the order of HE is equal to order of HA1 is equal to order of HA2 and so on. Order of HAN minus 1 is equal to what happens from this statement? This statement says that any two right cosets consisting same number of elements, which means that all these right cosets are consisting same number of elements. How many are there? Coming to this, what is the order of H here? M. H is itself a left coset as well as a right coset, because we can write H is equal to H and EH is equal to H. We have in this case right sense, in the sense of right cosets. H is equal to H and order of H is equal to M, then each right coset consisting how many number of elements now? The number of elements in H. Let it be 1. Now, since G being finite and it is a set consisting all these elements E, A1, A2 and so on, An minus 1, for each element we can write a coset again, and among these cosets, how many are there? There are exactly n cosets. If they are disjoint or identical, we don't know. Let us see some example here. G is equal to 1 minus 1 I minus I. This is the group. How many elements are there? 4 elements. And suppose H is equal to 1 minus 1. This is the subgroup. We can write the cosets of H as H1, Hi, H minus I and H minus 1. From these cosets, only these two are disjoint cosets. You may observe this in the example, whatever given in the last lectures. You may observe that H1 and HA are only two cosets which are disjoint. Among these 4 cosets, the disjoint ones are only 2. Okay, right? Not all are different. Some of them are different. Let them, for our convenience, among these n cosets, H, HA1, HA2 and so on, H, AK minus 1 are the disjoint cosets. Now count them. How many are there? From this we can count it as K minus 1 right cosets, and including H, there are K disjoint cosets. How many are there? K disjoint cosets of H and G. Again, we have another result is that every group can be expressed as union of disjoint cosets. What is the meaning of it? Suppose G is our group, which says that, this theorem 2 says that G can be expressed as union of disjoint cosets. Among these n cosets, how many are there disjoint? K. So, K disjoint cosets union is nothing but our group G. So, H union, HA1 union, HA2 union and so on union HAK minus 1. Now, we observe that G is now expressed as union of some cosets. That implies, let us consider order of G, which is nothing but order of, what is G now? It is the union of some sets. Simply we call it as a union of some sets. Union HA1 union and so on, union HAK minus 1. Again we have a noun formula is that how can you calculate a number of elements in A union B set? This is nothing but number of elements in set A, number of cell plus number of elements in set B minus number of elements in A intersection B. It says that number of elements in union set can be written as number of elements in first set plus number of elements in second set minus number of elements in the intersection of both the sets. This is the noun formula. From this we can write right hand side value as order nothing but number of elements, both are same. N indicates order, order indicates n. So we can write here order of H plus, because here is union of some k sets, here only 2 sets are there, here k sets are there. By using this formula we can write it as order of H plus order of HA1 plus and so on, order of HAK minus 1 minus order of their intersection, isn't it? What are these sets? They are disjoint cosets. What is the meaning of disjoint cosets? They have no common elements. If they have no common elements, what is the order of their intersection? Intersection set does not consisting any element, then how can we calculate the order? Simply it is empty set. Empty set does not consisting any element, so the value is 0. Now this is equal to, what is this value? From equation 1, the order of H E is equal to order of H, which is equal to M, isn't it? Plus order of HA1 is also M, plus and so on M. How many times it is added? Calculate. Close first one and calculate other ones, A1, A2, A3, HA1, HA2 and so on, HAK minus 1, that means they are K minus 1 cosets plus another coset. So totally K sets. K sets order is added, so K times M is added. Now this value is equal to K into M, where K is nothing but an integer. K is nothing but an integer. What is left hand side? Order of G is equal to, now expressed as an integer multiple of M. Integer multiple of M. It is only possible whenever M divides order of G. What is M? What is M? Yes, this is nothing but our subgroups order. That is nothing but order of H. That is order of H divides order of G. Now observe, the climb is over in this case, isn't it? Right. Now coming to the case 2. What is the case 2? It is about improper subgroups. Let H be any improper subgroup. Improper subgroup. Then the format of H is either singleton E or it is identically equivalent to our group G. isn't it? Okay. If H is singleton E, then what is the order of H? Because it consisting only one element, so order of H is equal to 1. We know that 1 is a factor of every element, every number, particularly our n. That implies, what is 1 here? Order of H, which divides n means order of G. In the case of singleton E, we had already proved that order of H divides order of G. What is another subcase? That subcase is nothing but whenever H is singleton E, we had proven the result. If H is equal to G, then what is order of H? Is evidently order of G. What is this value? This is n. We know that again every number is itself a factor. So n divides n. That implies order of one sense we can write n as order of H and another order of G. Here also we proved that order of H divides order of G. From case 1 and case 2, we confirmed that the subgroup order divides order of G, provided G is a finite group. Hence, from case 1 and 2, the statement is true. What is that statement? Order of H divides order of G provided H is subgroup. H is subgroup. This theorem is known as Lagrange's theorem. Thank you.